Hello developers, let's start developing. I am Veko and this is the 17th task for the 2024 Advent of Code. And in this we get to do one of my favorite types of tasks and one of my favorite things. We're gonna use our computer to write some software that simulates a computer. By definition, it's recursive. So we have something that is a 3-bit computer. So we have 3 bits, which means we have 8 different instructions, and the instructions are add of a BXL, BST giant Z, this is a normal jump, not 0, BXC out, which outputs BDV and CDV instructions, opcodes 0 through 7, and all of them are explained. And so we have 3 registers in this computer, and then we have a program. So our input is the values of the initial registers and some program that we need to take care of. So parsing the input is gonna be a bit weird since we don't have the repeating thingy all the time, but we can do a bit of regexing in order to do that. So this will be register. Oh, we need to paste this here, and then our regex will be, well, let's start. Then we have register, which is A or B or C, and we can extract that. Then we have a colon, a space, and a series of numbers, which we kinda want to get. So if this is our input, we should match on the first, on the second, and on the third line. So it's gonna be straightforward now. So we get the lines, and we always have exactly fine lines. We're gonna have the register regex, and it's not that, it's this. So nope, we don't have the instructions are numbers, so we will need to basically, let's type our computer. So it has something like that. Only this is a number array. Actually, since we're here, let's transform it, because all of these are actually pairs of instruction. This is one pair of instruction, this is one pair of instruction, this is one pair of instruction. And let's do that in the parsing part. But no, let's take it one by one, because we have no idea what the second part will be. So we have that thing. So of course our input is not gonna be a string array, it's gonna be a computer. So we have the register regex, and now we can have, we can take the register A. So we're gonna run that line on lines of 0 dot match using that, and once we match it, this will return a regex match array. We're gonna take the second part, and this returns a string, maybe. I'm gonna say, well, I know that there is one, and then I will just parse int it. So this is relatively fragile code. It depends on a lot of things, that we have a first line, that we have a match, but if anything, any of this returns undefined or 0 or blowups, then we have some kind of a problem. We have the B register, the C register, and then the program. So for the program, let's have it like this. So we have our program, column, space, and then a set of numbers followed by a comma, and we can have that multiple times. And then we have a set of multiple numbers. But to be honest, this can be more than a single number. But we don't want to catch the first number, we want to catch all of those. So we will add parentheses here, and we have our groups. And of course the string ends there. Let's have it like that. Of course we can basically slice off the program part, but to be honest, I kinda like it with the regex better because it's more flexible. So for the program we would have two lines of not 3 but 4 because we have an empty line, and we're gonna match it with the program regex, and we're gonna take the first group, we're gonna split them on a comma, and then we're gonna map them using the %, which will give us an array of numbers. So now we can return our computer. We have all the data that we want. So registers, come on, you guessed it correctly. Yeah. So A is the A register, C B register, C register, the pointer, instruction pointer is initially at 0, and this is our program. And now I will just say console.log our input, return -1 so that this thing works. We can also return -1 here, but we can also turn off this part 2 and result 2 and test whether we are parsing our input correctly. $729.00, and the values that we inputted are 729 and 0 and 0. And then we have 015430, 015430. Great! We have our computer. Now we just need to run it. How do we do that? So, since each of the commands is 2 letters, so we're gonna say, well, yeah, exactly this, while the computer is running. So a computer will run until its instruction pointer went off the deep end of the program. So yeah, we're not gonna do that. It basically hallucinated a lot of things. So, but we will do this. So we're gonna run our program until it stops. And if there are any loops, we will move the instruction pointer right and left. So we need to get the current instruction. And when the current instruction is at the point of input.program of input.pointer. And then we will get the parameter. And that is input.program of input pointer plus 1. So the next one is the parameter. So this means instruction 0 with parameter 1, instruction 5 with parameter 4, instruction 3 with parameter 0. And now I will have basically a dictionary. Not execute instruction is way too general, but I will have a instruction set. No, yeah, that could be okay. And this will be a record of a number that signifies the instruction and a function that will actually apply that instruction. What type should that instruction have? So we will get, yes, something along this line. We already know which instruction is, so we're getting the input, which is the registers and the instruction pointer, or do we only need the registers? And then we're returning, yeah, I like this better. So we're starting with the computer and a parameter, and we're returning the thingy. So this will have an instruction execution. And so we will have something like 0 is do nothing. Why are you complaining? This should, oh, we should return the input. Yeah, this is okay. So now, and so on until 7. So what we will need to do is, so we have the instruction, we will need to find the const process, let's call it. We will need to find the instructions, the function that we need to do for that instruction set, and then, yeah, we can do this, but just as an error precaution. Otherwise, we are reprocessing the input, and I quite don't like this. And note that we cannot just do this because the registers are a nested property because we designed it that way. So I will just have to say that registers are input dot registers, then yeah, we can copy over everything else. So this effectively makes this computer a copy of the input so that we don't destroy it. And we're not using the input anywhere else, we shouldn't be. So this will be computer, 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 computer. So, yeah. Yep, we need to declare it like this and not the other way around. Otherwise, we would rewrite the registers. Yeah, once again, TypeScript is correct. Let's see where we are using the input. Only in that part, we're not using it in this part. And now we will need to implement these actual thingies, and we have exactly 8 of them. So the first, and we can treat them as kinda independent. So one more thing, there are two types of operands. The sum of them can be a literal operand, and a literal operand is if the value is 7, it's 7. Yeah, that's the example. But we have also a combo operand, which means if it's 0 to 3, it's 0, 1, 2, and 3. 4 means the value of register A, 5 means the value of register B, 6 means the value of register C, 7 means basically halt and catch fire. So let's implement one of that has a literal. Yeah. we can do the bitwise XOR. How do we do the bitwise XOR in JavaScript? It's actually here. No, not a bit shift. This is a bit shift. We don't want to do that. Let's ask Google. Oh yeah, I forgot about this. We do have an operation for that. So we can just use this operator that I've used like twice. So yeah, we can do that. Let's go back to the definition. The BXL instruction, opcode 1, calculate the bitwise XOR of register B and the instruction's literal operand, then stores the result in register B. So, which means that we're gonna leave 1, 0, but let's implement what 1 will be. So, we will need to take the first argument. Actually, we're gonna do a lot of copying because I want to do that. So I will define a function that says copy computer. That gets a computer and then returns this. So we're gonna need to use it. We can actually use it here, and it's much simpler. And if we add some weird things to the computer, we can just do that. So we have a parameter, and the parameter is literal. So the first argument is nope. The first argument is input dot parameter. No, the first argument is the computer dot registers dot b. The second argument is the parameter, because that's a literal. The value that we need to calculate is first XOR second. We need to put that value copy computer of the input on the result. We're gonna set the register B with the result. We're gonna change the pointer of the result to move 2 times over, and we're gonna increment the result. So I expect that most of this will have the exact same pattern. We will get the actual parameters, we will do an operation, and then we will do something. This is kind of boring, so I will skip this writing code. Yeah, let's get back to this when I'm done writing all the implementations. So some time has passed, and in the meantime I kinda implemented all of these other things. So we have the A divide when we're getting the values and we're dividing them, truncating, we're only working with integers. I had to implement a combo value, get combo value function, which basically returns the register depends on the value. I also added the output array to the computer so that we can see what is going on. This is a fun thing, the jump not zero instruction, because what happens if the register A is 0, then we move past it. Otherwise we are playing around with the parameter, with the instruction pointer, so we're moving it back. And this is the way actually computers implement loop. So we're going in a certain direction, we get to a condition, and that takes us back. So we're looping. Until the register A becomes 0, then we're not looping anymore. The thing, so right now I do have this implementation and it will output what I needed to output. So now I will just take the big input. It doesn't look too big, but it could be, and run it. Note that these programs are kind of difficult to analyze. In general, programs are difficult to analyze. For example, if we have this kind of code, while false, do something complicated, this is trivial, this just won't execute. But if we change this program with just one bit, this can become a whole other problem. So just by changing by one bit in the source code or something like that, we can have a program that is much more complicated. Anyway, we have the big input. Let's see what we get. I don't think that we will get too much input. We will get something like this. I have no idea what we did because I didn't analyze that. I did analyze the small example. This basically takes 729 and repeatedly gives us the modulo 8 of this number divided by 2. So it literally would start 728 divided by 2, take the modulo, divided by 2 again, take the modulo until 729 becomes 0 when the program stops. Let's see if we actually implemented our thing correctly. Yes, we did. Let's see what part 2 is. We already had in some previous Advent of Codes problem like this, and one problem, the part 1 was relatively simple. You implement a computer, it runs for something like 2000 steps, and it outputs some things. And then the second part was just, now change the value of the register A to 1. It was 0, we changed it to 1. That kind of triggered a program that ran not in 2000 steps, but in several quadrillion steps. So we had to analyze the input, we had to do some changes, optimization of the input so that we can have it actually run. It calculated some modulo of some power function, who knows. But let's see what this thing does. Output another copy of the program. Seems to have been corrupted. Okay. So now we need to run this thing into a loop. The program is supposed to be a quine. A quine is a program that outputs itself. So basically, if we start with this, we need to get this back. And we might need to do some analysis, but let's solve. I'm quite sure that we should be able to solve the demo example quite fast, and then we will try to basically reason about the demo. That's not the demo. That might be dangerous thing to do. So we're gonna start with this. So we have this program that says 035430. Is it the same one? No. 035430. 54 means output A. 30 means jump to the beginning if A is 0. And this will divide the thing with 2 to the third power 8. So basically, we're gonna start with this program and kinda run it. I will actually copy this and call this a special method, run program. It doesn't even need the debug, it just needs that, and we can, for the first one part, we can change it, run program of the input. So for the second part, let value equal 0. And we're gonna have the while true now. So while true, the computer will be copy computer of the input. Yeah, this is exactly what we want. Copy the input computer, set the register A to the value, run the program to get the output, and check whether the output is actually the input.program. Yeah, joined by those things. If it is, we need to return the value. Oh, I changed it so this thing returns strings, so we will need to return the value as a string. That's not too much of a problem, so we increment the value, and I will add a console log here. I will add an if here. If the value modulo 1000 is 0, then say trying value that thing. We should never get here, so a throw is appropriate. And since we already have value true, this part is unreachable. So let's see if we can get up to something here. No, because we're missing a comma somewhere, or a parenthesis in this case. And in order for the second part to run, we kinda need to include the second part. One 440. Yep, that's the original value, the correct value where our program becomes a quine. Let's try it on the bigger input. And let's add a couple of zeros here. So yeah, it runs relatively fast up to 100. So let's see if this thing, let's actually start with 1000. Because this is a bigger program, it might run for a longer time. No, it runs relatively fast, so let's try it with 100,000 and let it run for a while. If the answer is in the small millions, we might get lucky, but we might not. Let's wait for a while. So it's been a while. This thing is still going strong at 10 million. I will leave it. It doesn't bother anyone. But in the meantime, I kinda tried to use the powers of Excel to actually analyze the program. I will continue to so, and we'll see what we can come up with. So, for now, for a fact, we know that our solution is not up to 16 millions or so, and we have our kind of analysis of what is going on. The initial. Move A to B, modulo 8, then X or something, and do something. And I will try to stop it now and take another route. So this is our program. We need to make sure that we get to our program. We output our program. So I will actually write some code that won't loop too much. It will loop something like 50 times. So we will just do that. But at the any time that we receive an output, we're just gonna console.log. uh, failed with that output. Let's see if we can find some kind of a pattern. Actually, specifically, we're gonna look at the first value that we outputted. Why are we doing? Oh, yeah, we threw an error here. Let's just return for now. No value found. This might be better. So we need to look whether any of these outputted a 2. One outputted a 2. Actually, we don't have need the trying console log. We can comment this out as well. So let's take a look. This outputted 2. And let's build some kind of a semi-database. This outputted a 2. Got us a 2. 40. And 48, some even numbers, some odd numbers. Let's continue. Let's say we will only write if output that starts with 2. Then we're gonna console log it for the first 50 things. So we get 2, 2, 2, 2, 5, 2, 3, 2, 5. Let's do it for the first 500. Maybe we see a pattern there. There's a lot of 5s, but actually no 4s. And we can maybe see a kind of a circular thingy here, because 1 and 9 is 8 away, this is 8 away, this is 8 away, this is 8. No, this is not 8 away, but this is 8 away. Some of them are 8 away, some of them are not. This is 8 away and this is 8 away as well, so that might give us something. And we have around 10% of these starting with a 2, so there's nothing much. Let's see if we get better luck if we say starts with 2 or 4. When we have the first 2 digits and nothing happened, let's go move up to 5,000. Let's see if up to 5,000 we get any 2 4s, especially any 2 4 1s. Oh, we got a lot of 2 4 1s. So that's good. Let's go up to 100 and search for 2 4 1 5. 2 4 1 5, no 7s, actually 1 7. But so far I don't see a pattern except for the 8 connection. We do have quite a few pairs when they are only separated by that. But I don't think that we can actually jump through that. So what we want to do now is to guess what kind of number will actually give us something that starts with this. Because the problem is that we are getting some input for some values, and the length of the input increases. So if I say that the value starts at, let's say, 1 or 10 million, 50 million, and then give me a slice of 100 items, we got nothing that starts with that. Oh, we need to value plus. This needs to be this much, actually. Yeah, we're getting that the length of this thing is still way less than the length of this thing. On the other hand, why not try to kind of brute force this? We can process for any number, we just don't want to process for all of them. So it doesn't really make sense to do with anything under 50 million. Let's see what happens when we get to 150 million and we process 100,000 items. Yeah, we might get the solution, but in a very, very, very roundabout way. Did we get a bigger list? Yes, we did. It's a bit bigger. So we can say only give me those that actually start with this much of the source. 6 comma, yeah, let's put in the 0 and start with 750 million to that and 1 million. We might not get any values, but we are getting closer in the length of the output, because obviously the length of the output depends on the value of the register A. The bigger the register A, the bigger the value, the bigger the output. More loops we can go through the code. Because I really don't want to calculate this analytically, but I might have to. We didn't get lucky. Let's write this thing once more. Oh, let's have it here so we can have this as well. Doesn't really matter. And let's move a bit up in the world. So this has nothing to do with our input or our analysis, but we can see that it's getting actually not really longer. So I guess it will get longer when we move into the billions. Let's see how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is kind of connected with the number of digits that we have. So that would mean that we have billions, trillions, something like several trillions. So let's do it from 10 trillions to 10 trillions and a million. We're just looking at the length now. So this should have about 3 letters more. So we're gonna need a bigger boat. And we might even need to use big int numbers. Let's see how far are we with this number to a place when we're unsafe. So if I get this and give it 3 zeros and compare it with number dot max safe integer, I'm always thinking, when I'm doing advent of code, I'm always thinking about these values because they are totally important. Otherwise, we will get some very, very wonky results. And this thing says, kinda don't worry.